Thank you very much, and thank you very much for coming along this evening. Well, I'll get started straight away. This was my first exposure to extraterrestrial life back in the early 70s, when I was very small. It's the Clangers, and you can see in this picture, the Clangers are actually launching their first interstellar probe, known as the Iron Chicken, and I didn't realise it at the time. At the time, I thought the Clangers were rather lovely. But thinking on it now, when you look at their environment, which is completely airless, they're obviously very large, given the proportion of them to the radius of curvature of the planet that they're standing on. What we've got here is some gigantic organisms that can tolerate vacuum of space, the cold of space, hard vacuum, and they're also prepared to place very large amounts of explosive underneath their best friends. So I don't think we need to run into the Clangers anytime soon. They're a lot more sinister than they look. But what would real extraterrestrials look like? Well, after enjoying the Clangers for many years, I read an awful lot of science fiction when I was a boy. And here are some of my favourites from that period. And these are, Hollywood's best attempts, or science fiction writers' best attempts, to come up with what would extraterrestrials look like. And they're pretty fanciful things. I mean, I don't think there's a laser in there. This chap here from This Island Earth, you can see the rubber seams really clearly on his suit. It's a fantastic film, though, if you've never seen it. And the original The Thing, much better than any of the subsequent remakes. And he is supposed to be an animated, intelligent vegetable, but he looks pretty like a human being to me. And there are some other pretty recognisable aliens in there as well, I'm sure. But what would they really look like? Well, actually, I think the truth is they might be a bit more boring than that. Here is the results of a 200 million year long experiment which we did here on Earth, where what we did was we gave life oceans to swim around in and hunt fish in. And over here, this is the oldest contestant at 300 million years old and still going strong. Here is a shark. It's evolved to swim very quickly through dense fluids like ocean water. It's evolved to be stable in the water, so it's got fins. It's evolved to push itself through the water with a large caudal fin there, and its nice streamlined bullet shape with a mouth and eyes at the front, the business end, which can catch fish. 150 million years later, a reptile came along and did exactly the same thing. This is a mock-up of Ophthalmosaurus. There aren't any alive anymore. They went extinct a long time ago. But actually, it solved the same problem in exactly the same way, even down to the fact that there's a nice dorsal fin at the top there, and the curvature of the caudal fin. We know the maths now, and we know that if you've got a fin that shape, which is kind of like a crescent moon, you are a fast attack animal. And if you've got one that's more triangular in shape, you're a cruiser. And you kind of have to be. That's how the maths works out. Roll the camera forwards until only about 50 million years ago, and a mammal, which used to look like a pig, has evolved to do the same kind of thing. It went into the ocean, it became a fish hunter, and actually it looks exactly like these creatures. We call this convergent evolution. And I think it's extremely likely that wherever we go in the cosmos, we're going to find the same problems being confronted with very similar solutions. Take it a little bit further, you might think, well, they're all vertebrates, so they've all got to hang off of the same skeleton, brain, muscle sort of thing. Well, what about these? These are all solutions to propelling yourself through air. We've got a bat wing at the top, flat, thin membrane supported by little tiny struts. We've got a flying fish's wing down here, which is very, very similar, but evolved from a completely different biological resource. Sycamore seed, well, you can't get further apart than a bat and a sycamore, not really, and yet they've got almost identical solutions to the problem. Or, just for comparison, there's a fly's wing as well. So, 4 organisms here which are radically similar, if you can be radically similar, and at the same time extremely distant evolutionarily, but they've all come to the same solution. Why? Because there's usually one best way to solve a problem. But, having said that, I've got to make a caveat. Sometimes the problem isn't so obvious. You might be able to see there's a fish in there. There's a Sargasso dragonfish. It doesn't want to swim fast. It doesn't want to attack and capture other fish particularly. So it's gone for a completely different solution to the problem of being a fish. You've seen it, right? I hope you've seen it. There's its head and its eyes, and it's trying as hard as it can, all the way down to the length of its little curly tail down here, to persuade you that it's just one more piece of seaweed drifting in the Sargasso Sea. And it does a very good job. So, having told you that all fast attack fish are going to look like all other fast attack fish, maybe they won't be fast attack. Perhaps they have different problems in mind while they're evolving? I don't know. Where should we be looking for these things? That's a pretty important question. That's quite a nice picture of a star field up near the constellation Cygnus. You see there's a lot of stars. Could we look any closer to home? Well, back in the 1970s, when the Apollo program was going, all the best scientists in the world had come to a pretty straightforward set of conclusions about where we were going to be looking. We wanted somewhere where liquid water was going to be what was around most of the time. Didn't want to be frozen solid, didn't want to be boiling hot. We were pretty sure that acids and alkalis would be very harmful, so we wanted somewhere which didn't have a lot of dissolved salts in it. We didn't want any surprising toxins like arsenic or something like that. And we wanted it to be stable for long enough that evolution could proceed along its course without interruption. I say that was the 1970s view. Then, in the 1980s, we went here. This is not another planet. This is our own planet, but this is the bottom of the Atlantic Ocean. And down at the bottom of the Atlantic Ocean, you have the mid-Atlantic Ridge, which is basically a series of volcanoes at very high temperature and at very great depth. And this is a thing called a black smoker. And these are the sorts of conditions that you get around a black smoker. It's extremely hot. It's extremely deep, and the pressure is very, very high. So these are conditions that you don't get anywhere else on our planet. But you do get them on other planets, but not this one. And the 1970s wisdom would have been that this was totally sterile. There's no possibility of life existing there. But then we found life there. We found lots of it, and many, many different kinds. This one here is called a Pompeii worm, and hello there, come on in. It's got the kind of face that only a mother could love, but it's quite a large organism. It lives in water. It actually sulks if you drop its temperature below 80 degrees centigrade. So the kind of water that this thing likes living in would cause you serious injury if you jumped in to swim alongside of it. And really, why would you? But Pompeii worms are an example of a group of organisms we now call extremophiles. And extremophiles, we now know, are not confined to the deep ocean. Oh no, they're all over the place. There are extremophiles literally everywhere on our planet, in all kinds of peculiar environments. There's a lake in Northern California which has got very, very high levels naturally of arsenic poisoning. And yet there are microbes pretty much doing the backstroke in there up and down all day. They're extremophiles, they're very, very happy. They're extremely ancient, they've been around for a long time. And they turn pretty much on its head the wisdom of the 1970s scientists. So we've now got to revise our ideas. The 2017 answer is a little bit more liberal. We think they're going to need water. We're pretty sure they're going to need water, but we're not ruling out liquid methane at this point, although it's a bit extreme. They need some kind of energy supply, and we would have said not so very long ago that that has to be sunlight. But now geothermal energy from black smokers seems okay. Any kind of thermal gradient seems okay, so just a supply of energy, that's all we're going to say. And maybe they need a rocky planet, but we're not even too sure about that anymore. So we've got a much, much broader idea of where we think these things can live. Turns out there are loads of places just like that in our own solar system. I've listed just a few there, but there are many, many more. We keep adding to the list pretty much every month. But these are some of the things which were on the list when I typed this up just a year or so ago. Right. Here's one of my favourites. This is a moon called Europa. It's a little bit smaller than our own moon, which still means it's pretty enormous actually. And it goes around the planet Jupiter. And Europa's got, you can just see it in this beautiful photograph here. It's got a surface which is made up of ice, water ice, just frozen water. But the ice is cracked in these extremely long sulcuses, they're called. And they're a bit like the Grand Canyon or something like that, but made of ice. And they are red. We now know something about why they're there. It turns out that as Europa goes around Jupiter, another moon goes around Jupiter in about twice as long. So every couple of orbits, these two moons line up alongside of Jupiter, which means that Europa gets pulled gravitationally by the other moon. And it's a bit like if you go to Charlton Plasticine and they mash it, and then they mash it, and then they mash it. We now know that the crust of Europa flexes up and down by a good 20 metres during this orbital cycle. That doesn't sound like a lot, but actually that's a tremendous amount of heat energy being added to Europa, which means that the ice is permanently melting and permanently reforming. And these cracks are actually stuff welling up from the oceans underneath. Now, we're still not entirely sure what's under there. We're very, very interested in the fact that it's got these strange organic colours. That's a pretty good indicator that there's a very complicated set of chemicals going on there. There are some theories about what Europa might look like if you slice through it. For a start, we know it's got this ice surface. We know it's got all the rocky cores and things like magnetometers on the space probes have told us that. What we're not too sure about, what the argument's all about right now, is this ocean just here. We think it's very likely that there's some liquid water between the ice and the rock. Some groups think maybe it's just going to be slushy, semi-liquid ice, not very exciting. Some people think it's going to be pretty much clear water. The volumes that we know about mean that there's actually more water on Europa than there is in all the oceans of planet Earth. So, in one very optimistic view, Europa is this gigantic, dark, black ocean with nothing but ice skies above and rock below, and perhaps as much as 20 to 50 miles depth between those two extremes. Might be that nothing at all is living there, but something's making those red organics and something is coming up to the surface. So we'd like to know a little bit more about Europa. It would be a really good place to go. And what good news this is, we're going there. This is straight off the drawing boards. This has gone into design just this year. It's a thing called the Europa Clipper. NASA will be launching it in the 2020s, and it will be having a really good look at Europa. And so by the time some of the people in this audience are, well, only half as ancient as I am already, we should have much more data about Europa, and we should have a much clearer idea of whether or not anybody's home on that world. There was talk for a while, no, actually I'll get onto that in a minute. Let's go somewhere else. This has been in the news quite a lot recently. It's another ice moon. This one's going around the planet Saturn. There are a lot of ice moons in our solar system. They're extremely common. All the gas giants have them. Pluto is in effect an ice moon all by itself. There are lots and lots of these things around. Enceladus, we thought, was pretty boring. It's the brightest object in the solar system. It's an ice surface. It's very reflective. So we figured that it was a dead world. But when the Cassini probe just got into just the right position, it saw something quite strange. It saw these plumes of water jetting up from the southern pole. And it turns out that Enceladus is blasting water into space from beneath the ice. And again, it's tidal heating. It's this idea that the moon is being flexed by the orbits of other moons that's keeping the liquid under there, the water under there liquid. And this is very, very clear indication this is happening. Just to give you the scale, these plumes here are a couple of 100 miles high, so they're being blasted out with some force. Nearly all of that material falls back onto Enceladus and recoats it and refreezes, which is why it's so bright and white. But underneath there is a liquid ocean, and it's at the right temperature, it's probably got the right materials, and so it's very, very likely that Enceladus is host to life. Unfortunately, we're not going there anytime soon. What would be great would be to arrange a flyby through one of these water plumes and to actually sample the plume in situ without having to drill down through the ice. So it would be great to build a mission like that. But in order to get a mission to Saturn, well, first of all, the flight time is very long. It's a good 8 to 12 years. The build and design and construction phase adds on another 12 years. So even if we said go and we push the button tonight, nobody's going here until the 2030s, maybe the 2040s, which is a pity. But some of you will certainly be around to see the results of a mission to Enceladus, and I hope it's really interesting. The great news about the Europa Clipper, just to go back a couple of slides, is that we've now discovered that there are also plumes of water coming out of Europa. So there is an opportunity to fly through those, and that is something that really can happen in the time frame of the next 10, 15 years. So we might get some good data from the under ice oceans on Europa even so. So that's really exciting. But what about further out? There's a lot more space out there, as you can see. This is just a tiny part of it. Just to put that in context, that's the constellation Cygnus again. You can cover it with one hand quite easily on a nice summer's evening here in Britain. So there's a lot of stars covered up in that one hand field of view there. how could we possibly find life out there anywhere? Well, first of all, we've got to know a little bit about stars. Stars come in all shapes and all colours and sizes. If you're a yellow star, you're a G-class star. The Sun happens to be a G-class star, so I'm biased, which is why I started with a G-class star. You get very large ones, like Kepler. You get small dwarf ones, like our own Sun. You might have cooler ones. These are the economy class stars of our galaxy. These use their fuel very, very slowly, and they burn away at a nice, gentle, low rate for a very, very long period of time. At least the one on the top does, the little red dwarfs there. And red dwarfs might live for hundreds of times longer than our own star is going to survive. Or you might have a red giant star like that, which is what our own star will turn into at the end of its life. But again, you get red stars up there in space. We're very interested in the red dwarfs right now. You also get the young hotheads, the profligates, blues. They burn their fuel at a ridiculous rate of knots. They're not around for very long. They're probably not around for long enough for life to evolve around them. So most people have ruled out the B or A class stars as a host for life, but perfectly happy and willing to be proved wrong. Well, if you're in orbit around one of these stars, you're going to collect some solar radiation. And stars have got what we call the Goldilocks zone around them. And a Goldilocks zone is basically, if you're too close to the star, you're too hot, something like Mercury, and you're just going to get baked, no possibility of life. If you're too far from the star, you're going to be frozen solid, something like Ceres, and in that case, you're still not going to have any possibility of life. If you're just the right distance, like Goldilocks and her three bears and the porridge, if you're just the right distance, then liquid water can persist on the surface of the planet, and you stand a chance of hosting life. It won't surprise you to know that the Earth is a little bit to this side of the Goldilocks zone. Mars is just on the edge of it, and Venus is just on the inside edge for us. So the Goldilocks zone for a yellow star is generous, and there are 3 planets kind of in it here in our solar system. If you're a blue star, you've got a bit of a problem. Blue stars, the Goldilocks zone is much further away, because the blue stars are burning their fuel so fast that they're just too hot and too powerful. Furthermore, one of the consequences of burning your fuel that fast is you release a tremendous amount of radiation, which our own star doesn't release. So these stars are going to get blasted, these planets are going to be blasted with radiation. And again, we think that probably blue stars can't host planets for that reason, or life-bearing planets for that reason. Red stars, little dwarf red stars, the Goldilocks zone is much closer, and these things have got to huddle really, really close to their planet. This is okay. The Goldilocks zone is very narrow and very, very tight, and it's so close to the planet that, so close to the star, these planets are probably orbiting in a matter of days or weeks, rather than the year or so that we expect. But there is still the potential of a zone there. One problem is that when you get this close to your star, you end up facing it all the time as you orbit. You actually rotate at the same speed as you orbit the star. We call that tidally locked. And the Goldilocks zone of a red dwarf is pretty much in the tidal locking phase. So chances are, if there's a planet around a red dwarf that's in the Goldilocks zone, it's got one side where it's day for 1 million years at a time. It's got the other side where it's night for 1 million years at a time. And probably the only really Goldilocksy bit is right on the boundary there. There's a suggestion that you can move heat using the atmosphere around these 2 bits, so a little bit of heat will flow into this side and maybe keep a band of it warm. But it's going to be a very strange world. Imagine living in a place where it's always sunset throughout the whole of history, or always dawn. They might be somewhere like that. We also know that red dwarf stars, like many humans I've known, have a fairly stormy teenagehood, and they have lots of sunspots and solar flares, so they may sterilize their own planets as they're forming them, which could be a bit of a problem. Okay, well, can we detect any of these planets? It'd be very nice to see some. This thing kind of can. This is the Kepler Space Telescope. It's up there in orbit around the Earth, and what it's doing is it's staring fixedly at just one part of the sky as it goes around. It never takes its gaze off of that one part of the sky. And it's monitoring about 100,000 stars, again in the constellation Cygnus. Okay, and it is a telescope, it's taking photographs of them, and it's looking for one particular event. There's the place that it's looking at. And I showed you a picture of Cygnus earlier on. So this summer, if you wanted to, you could find those constellations and you say, oh, I'm looking at what Kepler's looking at right now. And what it's looking for is an event like this. I paid an absolute fortune for these high-tech graphics. I hope you appreciate them. The planet is orbiting around its star, and it just happens that the plane of the orbit just happens to line up with Kepler's viewpoint, which means that the star seems to blink. In the top one, the planet is missing its star from our point of view, so we don't see anything happen. In the bottom one, what happens is what we call the light curve just drops down as the planet whizzes in front of its star. And you would see this regular bip of a light curve like that. Well, that's fine. And Kepler can do that. It can keep its little unblinking gaze on all of these hundreds of thousands of stars, and it can look for the light curve changes of each one, reports that data back to the Earth. Things get a bit more complicated if there's more than one planet. Then you're going to see lots of blippage. And you've got to do some pretty comprehensive maths in order to sort out the signal and analyse that, a thing called a Fourier transform. And they can do that. They've got very, very good ways of analysing this data. And what you get out of it is you get a planet which is winking out, or a star which is winking out for a certain amount of time, usually a couple of hours. The length of time it winks out for tells you something about how far away the planet is from its host. Once you know how far away it is, you know how long its orbit is going to take. Once you know that, you can start to point a different kind of telescope at the star called a spectroscope, and you can look to see if that star is wobbling backwards and forwards as its babies go around it, because they're pulling on the star just as much as the star's pulling on them, and so they wobble. And we can use a telescope to measure that wobble. It's really, really, really fine measurement, but we can do it, which means that we can get the time it takes to go around, and now we can get how hard it's pulling. In other words, we get its mass. Now we know what size it is. And once we know that, we know what density it is, and then we can say, is it a rocky Earth-like world or not? And all of this data can get wrapped up in there. So Kepler has been tremendously successful. Its first mission is over now. The way that they stabilized it in space was they had some little gyroscopes running inside it, and those seized up one at a time. It doesn't have enough gyroscopes left anymore, so it can't actually do the mission that it was first decided to do, but my goodness me, it's been successful. Back in September 2014, when I first gave this talk, we had a list of 8 Goldilocks planets the size of the Earth, and about, 1,826 planets. So wind the clock forwards a couple of years. That's the story as of March this year. We've increased our library of planets really substantially, and we're adding new planets to the list all the time. The thing that's really exciting is this bit here. We've now got 21 Goldilocks Earths. Now, most of those will be Mars or Venus. They will, in all probability, be completely lifeless. But 21, and we've only been looking for a couple of years. What's our library going to look like in 20 years' time? It's going to be pretty extensive. There are other missions going up there to have a look and see what else they can find in the same thing. And just to show you the rate of progress, this is how quickly we're discovering new planets. And you can work it out for yourselves pretty much. But we're getting really good at this now. And there are other ways of detecting planets coming on stream. Looking for the wobble is a really important one. Looking for, well, I don't want to go into all of those details actually, but looking for the planets as they're occluded by other objects in space, we can do that now. And we're actually getting this exponential increase in our ability to detect planets. So the library is getting, to be honest, it's getting a bit boring. I used to have a little app that let me know when a new planet was discovered. It was going, a new planet. No, new planet. But, you know, what a luxury that is. Let's do some maths. We think that something like about 1/5 of the stars that we look at have got planets, okay? And we know that there are about 400,000 million stars in our galaxy. It's really easy to throw out a number like that, isn't it? You know, what does that number even mean? I mean, just visualizing a million is pretty difficult. If I put a pound coin, I've got one. Audio-visual demonstration. If I put one of these new defective pound coins on the ground and said, you can pick that pound coin up and put it in your own pocket. That's yours now. That's an operation that takes about 1 second, assuming you've got a good back. Okay? So if the floor was covered in pound coins, you could go around and pick them up like a bird hunting for worms. No problem at all. If you had £1,000,000 coins, that would take you non-stop, if you didn't take breaks for sleeping, eating, going to the lavatory, or any of those other really vital and interesting functions, it would still take you 11 days non-stop, 24 hours a day. That's 1,000,000. Just 1,000,000. That's what 11 million seconds actually looks like. Sorry, that's what 1,000,000 seconds looks like. If you wanted to extend that out to do all the stars in our galaxy, you would be picking up pound coins, I think, for something like 350 years. 1 a second. Blip, 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 blip. It's a lot of stars out there. A tremendous number of them. So let's say that 1/5 of them are sun-like. Quite reasonable. Sorry, beg your pardon. Let's say that 1/5 of them have planets. Let's say that 10% of them are sun-like. That would mean that there was something like 8 billion Earth-like planets out there. We've discovered 21 so far. We've got a little way to go yet before we've seen all of them. But that's just the straightforward bit of the maths. Let's go a bit further. We can just totally guess this. This number will change if we find life on Enceladus or if we find life on Europa. If we only find life once in our solar system, across all of those rocky moons, across all of those planets, then we know that life is really difficult to produce, and we know that we've got a bit of a problem. But if we find it twice, or even 3 times, or who knows, maybe more times, just in this one solar system, then the conclusion would have to be that life is really quite easy to get going, and that it happens a lot. So my diagram there of one Earth surrounded by lots and lots of Marses, it's a total guess. We don't know yet. And we will have a lot more data on that really soon. So let's just make the number 1 in 1,000. Keeps it nice and easy. That means that there are 8 million planets in the galaxy which have got living things on them tonight while we're doing this talk. 8 million. That's a lot. I hope I've got my maths right. James is my checker on this one. I'm pretty sure I'm okay, but I'm very happy to be corrected. I'd like to see some of those. Not going to, but I'd like to. I mean, what do they look like? This is one that was announced a couple of weeks ago. This is the famous TRAPPIST system. Have you guys come across this in the news? Yeah. It's extraordinary, and the reason it's extraordinary is because the Kepler data gave us 5 Earth-sized planets in one system. I think it was 5. No, so 1, 2, 3, 4, 5, 6, 7. Sorry, 7 Earth-like planets in one system. Some of them are on the inside of the Goldilocks zone. Some of them are on the outside, but a bunch of them in the middle are right in the Goldilocks zone. I think they're declaring 3 as being Goldilocks planets. They then hired their most imaginative artist to paint pictures of what they look like, because we do have a bit of a problem with this. They're very helpful for illustration there in the picture, just in case you were thinking that we've got photographs like that of them. And this is the problem. You can see the planet, can't you? It's right there. These planets are very, very dim because they just reflect light from their parent. The parent, on the other hand, is extremely bright. And it's a little bit like going over to Flamborough Lighthouse and putting one of those little LEDs from your bike on the Flamborough Lighthouse, and then coming back here to York, getting your binoculars out, and can you see the LED in the glare of the lighthouse? It's that kind of effect, okay? So we have a really hard time actually seeing planets around other stars. And as it currently stands, nobody ever has. There's some infrared data, which is quite good for that, just around 1 or 2, or what we call protostars, or protoplanets. But real planets like those, no, we haven't got those yet. But maybe this will get them. This is the imaginatively named European Extremely Large Telescope. It replaces the European Very Large Telescope. And it's down in Chile. And there's every possibility that this might actually be able to take photographs of these planets. It's certainly got the capacity to do the resolution that we need. It's not built yet. Looking forward to it being built sometime soon. I'd like to go and visit it if at all possible. Or there's a replacement for the Hubble Space Telescope. It's called the James Webb Space Telescope. It's much, much bigger than Hubble. These yellow hexagons are the mirror that it's going to use to collect light. And the Hubble telescope, the mirror was only one of these hexagons big, pretty much. So this thing has got a much, much larger light gathering capacity. It's absolutely enormous. And that's going to be launched in the not very distant future. And that stands a very good chance indeed of seeing planets around other stars, which would be nice for us. But there are some problems. Just because they're alive, it doesn't mean that they'll be able to talk to us. Just look at the history of the Earth. Let's assume that the Earth is fairly typical. For most of the history of life on Earth, there's been nothing here but bacteria. A sort of bubbling noise, a boggy sound. That's all there's been. That's the blue bit, going all the way up to just 600 million years ago. This is when life decided to stop being bacteria and became multicellular, but was still stuff that, I'm thinking about things like seaweeds, and I'm thinking about things like little tiny plankton and stuff like that. Things that couldn't possibly build a radio telescope and are very unlikely to launch a space probe anytime soon. Then life crawled up onto the land. It finally noticed that there was some dry land, so up it came onto dry land, and it developed into plants and animals that could walk around. And then we end up here with the kind of life that actually we can relate to. These are things like dinosaurs, things like reptiles, things like mammals, all coming in this little bar just here. So if we had visited the Earth at any point in the history of life here, except for this tiny little bar just here, there'd be nobody to talk to at all. And in fact, I challenge you to strike up a conversation with a dinosaur. I don't think it'd be very easy. You might just be able to see there's a tiny little bit of red just at the top there. That represents our tenure on Earth as a species. And I'm being really, really generous with the scale here. This is how long Homo sapiens sapiens has been around. And they actually say that if you make the history of life on Earth, the gap between my outstretched hands now, the whole history of the human race, from the pyramids, the Roman Empire, the Greek discoveries of mathematics, and so on and so on and so on, is about the same thickness as your fingernails we've grown tonight. That's us. And the rest of it is bacteria. Sorry guys. Historically, Earth is fantastically boring. And we haven't been around for very long at all. Even when we were around, we didn't do very much that was interesting. The Stone Age lasted for a ridiculously long period of time. And all we did was just bash the rocks together, guys. You wanted Douglas Adams, you got Douglas Adams. Okay, and that red bar there, if I expand that outwards, okay, even when we stopped bashing the rocks together and we started melting them instead, for a lot of that period, we didn't do very much that was interesting at all. We just made them into sharp things that we could hit each other with repeatedly. So there's the Bronze Age. That lasted for a long time. The Iron Age. Being very liberal with my dates here. This is what I think of as the modern age. And by modern, I mean everything after the Normans. So still talking not particularly modern. And then again, the little red bar, discovery of the electron, discovery of the electric field, discovery of radio, things like that. Our history of us being able to talk to anybody is ridiculously short. So most of the planets that we go to, where life will be, we will find nobody to talk to. But how long does the red bar actually last? That's limit number 3. Is it possible that we're going to do something so daft in the next couple of decades that we're just not going to be around to talk to anymore? Only time will tell. Most people are optimistic about this. Most people believe that if a civilization can temper its urges to play with all the really dangerous toys, then actually maybe they will last for a very long time. And once you've tempered those urges, then you're probably somebody who's fit to talk to. I hope so, but that's quite an important consideration. Space is pretty big. That's a consideration as well. Second Douglas Adams reference. And so if we wanted to talk to the Clangers, for example, and they're 2,500 light years away, which is not an unreasonable distance, then our message, travelling at the speed of light, will take 2,500 years. So we could send off the message at the start of the Bronze Age. Stonehenge has been finished and is in regular usage and what have you, and it would be something like, "Hello, Clangers, how are you?" And then over here, the message gets there around about now, and the Clangers go, "We're fine, thanks, how are you?" And back comes the message, and it takes us 5,000 years to have a round-trip conversation. There's very little chance anybody's going to want to do that. So we had better start talking to people who are a bit closer to home. Have we got any signals powerful enough to reach the Clangers? There's only one signal that we've been broadcasting regularly that can do that. And I think it's a real testament to our civilization that it's TV. TV broadcasts are strong enough to penetrate interstellar space. And my little blinking arrow is how far they've got. So we are currently communicating with aliens within that arrow. And they're currently watching reruns of I Love Lucy and Hancock's Half Hour. And I hope they enjoy them as much as I do. So one of the other limits on us is just how big space is and how far away all these little creatures will be. Another one is this. This is quite scary. What if we're the bacteria? What if we contact a civilization where they had their red period quite some time ago, and they're now in, let's call it the golden age, the phew, we didn't blow ourselves up period of history. How big could that be? What could possibly happen? I guess you've got to look into the historical record for what happens when advanced civilizations meet other civilizations. Who wins? Who comes off best? So this is possibly what happened. And it didn't end well for the people on the lower end of that scale, unfortunately. So there is genuine concern about what happens if we do contact a species which is actually so far ahead of us that all they can really offer us is a means of our own destruction. It's not impossible. So that's another limit on what we think we can achieve. However, we've started trying to look for them. We started trying to communicate with them. We have, for example, back in the mid-70s, sent out this handy long-playing record. 33s were pretty popular back then. And this one's got Chuck Berry on it. And it's also got Jimmy Carter, the then President of the United States, issuing a greeting to E.T. It's that one's stuck on a space probe called Voyager. And my favourite are the plaques which went out on a series of space probes just before that. There's the Pioneer 10 plaque, which, as you can see, there's a really scary amorphous spider entity, which is actually, it's dominating all of the inner solar system here. And so this is the planets of the spider aliens, and it had stuck 2 of these organisms as samples on board that and sent them off into space or something like that. I don't know what ET is going to make of that. I certainly don't think I understand it, but that is on its way to a star not terribly far from here, and it's going to arrive in 30,000 years' time. And it's up to the aliens to work out how to decode it. My best guess is that we'll probably overtake it, and it'll become a very, very valuable collector's item at some point in the future. But we are making attempts. We've also beamed out simple digital messages from radio telescopes into space, but to do it with any success, you need a tremendous amount of power. Power is expensive. Building the telescopes is really expensive, so our attempts to do that are very limited at the moment. We do listen. That is the Allen array in California. It's under construction right now, but it's already listening. What they do is they just add extra discs. With radio telescopes, if you have 2 discs next to each other, you can wire them together, and now they're one radio telescope. You can keep on doing that. You can keep on adding and adding and adding. And so the Allen array is busy listening to outer space. And it's sampling many, many frequencies in the hope that perhaps they'll pick up extraterrestrials' radio messages. It's not impossible. Here's a signal that actually was sometimes the famous WOW signal. And the WOW signal, I think, was intercepted in 1974, not by the Allen array, but by a different telescope. And the researcher who was looking at it, you can sort of see the data coming in off of the radio telescope with signal strength, and then suddenly he hits a 6 and a 7. Really, really powerful signals compared to the other signals. And when they looked at the region of space where that signal had to be coming from, there was nothing obvious there. So it really was, wow. Was that a blip from ET? It never got repeated. Nobody ever heard from that blip again. And they scanned that piece of sky again and again and again. Nothing ever happened. Was it a blip from ET? Unfortunately not. It was actually, we believe now, it was a comet which was actually only discovered in about 2008, which had made an orbit through that piece of space before. And we think it was probably just a radio reflection from that comet. That's why you've got to be so very, very careful with all of this sort of thing. But nevertheless, it caused a great deal of excitement at the time. Does anybody know who or where or what KIC 8462852 might be? This I find very interesting right now.
Is this the one about Stephen Hawking?
I'm sure Stephen Hawking knows all about it. Yeah, it's also known as Tabby's star. It's interesting enough, it's in the constellation Cygnus. It got picked up in the Kepler data. And it's a star that has gone dim by a very, very large amount for no good reason. We're not at all sure why. The most likely contender for an explanation is that it's a bunch of comets which are occluding the star with a cloud of dust. But actually, when you do the sums, the number of comets seems a bit improbable, what with it being 68,000 of them, and they all have to be giant comets at the same time. So another possibility is that maybe extraterrestrials are building something really, really big around that star. There's an idea of a thing called a Dyson Sphere, which is basically when there will come a point when we need every drop of power we can get out of our sun, and all the solar energy that's produced we will use. The only way you can harvest that is you put a shell around your star. Dyson Sphere would be extremely difficult to build. We certainly couldn't build it, but maybe a golden age alien species could. And so it's just possible that Tabby's star has got a Dyson Sphere around it. But I would give it a probability of 1 in a million, something like it's probably comets again. They seem to get everywhere, these comets. That was a really very, very quick romp through the topic. So there are my friends the clangers again, waving off the iron chicken. And I'd really like to offer the floor now to anybody who's got any questions and see whether or not we can open out a bit of a discussion about what we all know and share. Do we want to take questions before saying goodnight? So does anybody have anything they'd like to open up with? Yes, sir.
In terms of ingredients, like you had on the list carbon, is that still the main candidate?
Carbon's a really good candidate. Silicon is another one, but the lovely thing about carbon is it's the kind of the best Lego brick in the box, and it can combine to form so many other compounds that you get this gigantic suite of possible molecules which you can build into living organisms. The next best contender is silicon, but the suite is much, much smaller. It's reduced by a couple of orders of magnitude. So carbon really is our best bet, we think. But there'll be an organism right now giving this lecture with liquid chromium blood on a titanium-only planet somewhere, telling me that carbon is impossible. So I'm not ruling anything out, but I like carbon for that.
Well, if you look at the probability distribution, and if you think about it, the general trend shows that we're most likely in a larger group, where if you separate it into categoric groups, we're most likely to be in one of the larger groups.
Of
Essentially of extraterrestrials.
Okay.
And it's generally the assumption of the probability distribution forms a zip curve.
Yeah.
Now, if you think about it in that sense, then that means that there are bound to be a large amount of smaller groups of separate planets with very different conditions.
Yes.
So that means that while life could converge and evolution could converge on all of the groups which are similar, doesn't that mean evolution could result in a completely different under the different circumstances?
I see what you mean, but the sort of things that I was referring to are kind of really low down, really, really basic fundamental laws of physics. Things like hydrodynamics or things like friction, stuff like that. So there's no real obvious way around those rules. But you're right, there may very well be chlorine-breathing reptiloids on some, but they will be the oddities. I think most life in the universe is very likely to be very similar to ours, in terms of its chemistry, certainly, because there are only certain number of ways of making a living as a living organism. We know of 7 here on Earth. We represent one of them, plants represent another. So we've mapped out those pretty well. Some of them are really strange. 20 miles down there are some creatures which oxidize iron really, really slowly, and that's how they're releasing their energy. So but they're bacteria. They don't seem to develop radio telescopes yet, and they're not likely to. But they are interesting organisms. I think that's what you're getting to, isn't it? Yeah. Has anybody else got anything that would? Yes.
How would we actually talk to them? What language would we use? Would we just use maths or something like that?
I think we'd have to just use maths, wouldn't we? And the first thing we'd do is we'd establish, do you also believe that 1 plus 1 in binary equals 2 in binary? Yes. Exactly. And so that it has to start there, doesn't it? And maybe we get to Pythagoras' theorem pretty quickly in the hope that their space is flat too, because if they're in curved space, then we've got a problem. But that's how it's going to probably progress, isn't it? Certainly, hello, how are you? I'm having a lovely time. Won't cut the mustard, and whatever Star Trek says, it's unlikely to happen. Did you?
We've got lots of moons here in the solar system, like around Saturn and Jupiter. So, like with around Jupiter or something. So, wouldn't we have a higher probability of finding something elsewhere if we look for moons of other gas giants?
Gas giant moons are a really good target, and so there's a subdivision of the Goldilocks planet people, and they're people who are looking specifically for gas giants in Goldilocks zones, in the hope that some of their moons are therefore automatically Goldilocks as well. And so, yeah. In fact, I showed you earlier on the slide of the little red dwarf planets. Large gas giants in Goldilocks zones around red dwarfs seem to be quite common. And these things are extremely long-lived. So our planet is 5 and a bit billion years old. These things might be 20 billion years old. That's a lot of time for life to evolve. So it might be that moons around gas giants are the most likely place to find interesting things. We might be the anomaly. We might be the ones on your peculiar curve. Yeah. Yes, at the back.
What do we do if we find life and it's less than friendly?
Well, the great news is space is awfully big. I think we covered that one earlier on. And so it's only ever going to be a kind of slow email exchange at this point. The best technology we've got would get us to the nearest star in about 30,000 years, something like that. That's pretty slow for a news cycle. So I don't think we're likely to have a war or anything. Much more dangerous would be perhaps the contamination of ideas and new technologies, which they might send us, which we're just not yet ready to deal with or handle, or which just might make us feel really small and a bit, kind of what's the use? I don't know. It could go that way, couldn't it? It's very difficult to say. But I'm kind of hoping that the theory of relativity keeps us nice and safe, and that nobody can get here. There was a physicist called Enrico Fermi, who was a bit of an oddbod, and he was working at the nuclear research labs in Chicago, and he was having his lunch. And one day he just looked over and he said, "Hey, where is everybody?" Well, everybody was sitting around him having lunch. His whole team was there. And so one of them plucked up the courage, knowing that Fermi was one of the greatest geniuses of his generation, said, what do you mean, Enrico? We're all here. No, not you, not you. Where's E.T.? Because he'd worked out that in a galaxy this big, actually it should be possible for extraterrestrials to get here in 30,000, 40,000 years. The galaxy is an awful lot older than that, so why the heck haven't they arrived yet? And it became known as the Fermi paradox. We ought to be seeing evidence of extraterrestrials everywhere, because they've had such a long time to do everything. There ought to be Dyson spheres everywhere. There ought to be evidence of mined-out planets. Somebody's initials should be written on our moon just for us to find. All of that should have happened. And none of it has happened. Maybe we're the first. Maybe intelligent life is incredibly rare. And with that little glimpse of our own history where I showed you that tool using intelligence is the merest fraction of a fraction of a fraction of a percent of the history of the Earth, perhaps we're the fluke. And what we were always meant to be was kind of about as bright as dinosaurs. It's possible. Yeah.
I was reading in the news this week, and it's been postulated quite a few times that perhaps Earth was seeded by somebody who's in their golden age but they've left, and that when we do go around and look at all these moons like Europa and Enceladus, what we'll find is we'll find evidence that they were in our solar system and have gone.
I'd love that. That would be absolutely. If we go to Enceladus and it's got exactly the same DNA base sequences that we have, and if it's using very similar enzymes to the ones we use, then that is a massive, whoa, look here, this is really odd. And that would be a very, very big surprise. And it's certainly, if we do see that the chemistry is almost identical to ours, then we kind of have to conclude that they come from the same rootstock. But it doesn't have to involve ET. It could just be meteorites quite often smash off bits of the other planets. There's lumps of Mars all over Antarctica. There's lumps of Earth all over Mars. And so during that period, we might have sent our microbes to Mars. Mars might have sent its microbes to us. So we might all be Martians. They might all be Earthians, or whatever the phrase is. So it's possible that a solar system might only have one life form. There is one planet or one moon where that can't possibly be the case. And this is the thing I'd really like to finish on in terms of me gabbling away, but I'm very happy to take other questions. There's another moon of Saturn called Titan. Titan is not like the worlds I've been talking about. Titan has a very thick, hazy, smoggy atmosphere. The temperature there is kind of a comfortable minus 100 most days. And on Titan, water is a hard rock. It's as hard as granite is here on the Earth. So water is completely out of the question. There cannot be any water chemistry on Titan. But what they do have is oceans of liquid methane. And methane is the kind of gas, it's just natural gas, comes out of gas taps. But if you freeze it, you get a liquid. And for a long time, people thought there's no possibility of life on Titan. But then we settled a little probe down through the atmosphere of Titan called the Huygens probe. And it came down on a parachute. And as it was going down, it was sniffing out the chemicals on its way down. One of the chemicals it was looking for was hydrogen. And when it got down close to the surface, the hydrogen trace vanished. We went very, very low indeed. And all of our models of Titan's atmospheric chemistry said, no, that can't possibly be the case. There needs to be a nice even gradient. Now, a few years before the Huygens probe, two guys had written a paper, or not quite as a joke, but certainly as a kind of, wouldn't it be cool if kind of proposition. If there was life in a frozen methane lake, what food would it eat? And what it would eat would be hydrogen. That was the only fuel source that they could find at those sorts of temperatures. And so there's something on Titan using up hydrogen. We don't know what it is. And it's using it up in exactly the way that this paper suggested. And so maybe in these frozen methane lakes, maybe there is a kind of life which is utterly, utterly unlike anything that we've got. Really want to go there and find out. Unfortunately, it's around Saturn, which means we won't know until at least the 2040s. I should just about make that, barring accident. So it'd be nice to see, wouldn't it? It'd be very good. Have we got any other questions? Luke again.
One of the possible, I'm just wondering what the actual viability is of this, but in terms of communication of radio waves, small black holes are known to, small wormholes are known to exist at a very, very, very small level, to the point where they essentially they have no impact on anything because they basically
kind of in the string theory zone here, yeah.
Well, it's not quite string theory.
No, but they're in that sort of scale, I think.
Yeah. And if it was possible that you could actually realise where the space was being manipulated, you could, in theory, send a signal and a small enough radio wave signal through.
Yes.
Something along those lines. And would that make the communication barrier?
So long as both sides were playing the same game and they both knew that this is what they were looking out for. And the thing with the Allen telescope array, going back a little way, is I wonder if this is a little bit like the Yanomami tribe of Amazonian equatorial river deltas building a massive array of speaking drums in the hope that when the outsiders start using their drums, they'll be able to tune in and have conversations with them. We just don't use speaking drums anymore. And maybe ET doesn't use radio anymore. Maybe there's other ways of doing this, and that's kind of what. So we might never hear anything because we might be using the wrong tools to listen with, and only time will tell on that one as well.
Going back to Douglas Adams' analogy again.
Yeah.
Where the invading fleet is swallowed by a small dog.
Due to a disastrous misinterpreted scale. Yeah.
What aspects of scale might come into this as well in terms of too big, too small, etc.
Right. Planets are pretty constrained by size because if you get too small, you can't hold onto your atmosphere, and we're fairly sure that an atmosphere is necessary for life, or certainly circulation of some kind of planetary chemistry is necessary for life. So really tiny rocks, we don't think would harbour really tiny little creatures. And if you have a really massive, super rocky planet, then gravitationally, nobody's going to be leaving that because there's no way of getting off of it. And actually, life living on a planet like that would be under tremendous constraints. So I think there's probably a lower limit and an upper limit on the size that things can be. And would there be sort of giant star beings harvesting gas clouds out in space? You'd love to think so, but we're probably about the median size for the sorts of planets that we'd expect life to be on. If that's, yeah. Holly?
If we were to find an intelligent life form, how would we go about solving the ethical problem as to whether or not we would attempt communication?
There is a UN body that sits on exactly this issue. What do you say? Who controls the information? I mean, imagine if we get a wow signal tonight, and a real wow signal. Who actually is in charge of releasing that to the world? And the UN have kind of collared that and said, well, we need to control how that information flows out. But in today's era, I just wonder if anybody can control that kind of information anymore. There are too many ways that this stuff can get out into the wider world. So if and when it comes, it might come as a really big shock really quickly. Another part of your question, which I think you're also asking, is who controls what we send out? And right now, it was basically enthusiastic amateurs. Okay, NASA. But people who said, yes, I'll do it, I'll send a message out. There's nothing to stop you building a radio telescope and sending your own message out into space. But should you be allowed to? What sort of things should you say? Should you say, here we are, this is the limit of our nuclear arsenal, this is how far out into space we've got? Yeah, that would be quite a scary message to send, wouldn't it? A possibility, and I think this is quite an interesting possibility, is what if what you do is you use your radio transmitter or whatever to beam the instructions for building the kind of computers that you have. So we would send the instructions for building our best supercomputer. Then in your next message, once you're pretty sure that ET's built it, you send the entire internet. And you say, right, there you go, you've got our culture now. We're not coming to visit you because we can't get there, but at least everything we are has arrived with you now. And they send us their version of the internet. And so we actually communicate with each other in that sort of totality of exchange. And again, what do you want to send? And would it actually be a problem if we sent the wrong kind of information about ourselves? Big issue. I'm very glad it's going to be your generation that has to solve it. Is it? Lisa?
So with the Allen array, was it?
Mm-hmm.
Where it's a bunch of linked disks.
Yeah.
Would it be more efficient to build like some of these large supercomputer networks, where it's just if you got smaller, like if people own their own radio disks and you all connect them together, would it be more efficient or cheaper to have people have their own
Sort of crowdsource the search for ET? Yeah. Yes, although actually your best bet is to let them build the expensive bit, because you don't want that in your back garden, but then to let them give you the data, because the data processing of this stuff is enormous. They're sampling a really very wide range of frequencies, and they've got to perform signal analyses on all of these frequencies. So you're absolutely right. You can do it tonight. You can download the app for this. You can get extraterrestrial radio data on your computer, and you can be analysing it while you're asleep tonight. Your computer can be looking for ET signal. You might be the guy that gets the wow signal. And so, yeah, crowdsourcing this stuff is a very 21st century way to go, isn't it? Can we take just one more, please?
Well, linked to your comment about the physicist who over lunch said, "Where is everybody?" I'm sorry for this question, but could it be that they are here, but we can't see them?
No.
And what's the link between pure physics and the study of the paranormal?
That's, gosh, right, okay. Thank you. Let's end on a bombshell. Yeah, you're absolutely right. And in fact, I was watching a chap walking along the street just yesterday afternoon while I was walking my dog, and I'm pretty convinced he is an extraterrestrial because of the way he was walking. And I thought, gosh, what if you are? It's not a very good disguise, is it, mate? You could try harder. But getting here is really hard. Getting here undetected might be quite hard, although we don't know what kind of technology they've got. So who knows? Maybe it's really easy to get here undetected. So are we talking UFOs and that sort of thing, or?
Well, I'm talking that they might be sitting here right now because it might be instantaneous for them.
Yes.
And we just don't see them because we don't have that sense developed.
With a very heavy heart, and I do mean this quite sincerely, if I had that technology, I wouldn't come and watch me give this lecture. I'd be somewhere interesting, like the Battle of Waterloo or the signing of the Magna Carta or something like that. Those are the places I'd want to be. But you're right, maybe they want to observe the totality.
But is pure physics actually studying that and saying, is there a possibility that there's a sense that we don't possess?
Well, a lot of our equipment already operates in sensors that humans have never possessed. So things like magnetometers or interferometers, all these sorts of things. So we're already observing the universe in this gigantic and very, very broad-reaching sweep of senses that humans don't have. So yes, in a way, we are doing that. And I don't think we've ever seen anything that YouTube videos accepted. I don't think we've seen anything that makes you think, gosh, that's actually inexplicable in terms of what we currently know. And again, let's not rule it out. There also, if ET was observing us, they might not want to actually be spotted for the very simple reason that they're so humane. They don't want to run into the Golden Age meets Stone Age conundrum. I would do it if I was in their shoes. We can already build drone-like devices which can quite easily land on your little finger. So why not have some alien drones which are so small that they can live in your hair, or be on the food that you eat, or what have you? Maybe they're the things that they would be using to observe us, rather than actually being here in presence. So that's what I would do, because we can almost do it now. We'll be there in another decade or two. Sadly, it's rather scary too, isn't it? Yeah. Does that help at all? Does that answer the question at all?
Well,
No.
it makes me feel like we're all as clueless as each other.
Yeah.
It's comforting.
Yeah, that's true. Yeah. Gosh. Right. Well, thank you very much. I mean, maybe we could talk about that another time. I don't know, but unless there are any other questions, I hear the bells going, so I need to let you go home and get some sleep.